Okay, Harshita.
Good morning and good afternoon to one and all present over here. We are delighted to have Dr. Lucas Palatinus with us today. Dr. Lucas Palatinus is a renowned crystallographer whose pioneering work has significantly advanced the field of electron crystallography. He served as the head of the Laboratory of Electron Crystallography at the Institute of Physics of the Czech Academy of Sciences in Prague, where his research focuses on developing cutting-edge methodologies for analyzing atomic structures using electron diffraction technique. Dr. Palatinus earned his PhD from the University of Bayreuth in Germany, where his research centered on the crystallographic analysis of modulated structure. Following this, he undertook his postdoctoral work at the École Polytechnique Fédérale de Lausanne in Switzerland. Since joining the Institute of Physics in 2009, Dr. Palatinus has led efforts to refine electron diffraction technique for crystal structure determination. His expertise lie particularly in the application of three-dimensional electron diffraction, that is 3D-ED, and dynamical diffraction theory. Dr. Palatinus' achievements have been widely recognized. Among his honors is the Erwin Felix Louis Barthou Prize, awarded jointly by the European Crystallographic Association and the European Neutron Scattering Association for his exceptional contribution to crystallography. Through his work, Dr. Palatinus has significantly enhanced the utility and precision of electron diffraction, bridging the gap between traditional X-ray crystallography and the study of material at nanoscale. We welcome you, sir, to deliver your lecture.
Thank you very much for this elaborate and very nicely presented introduction. Thank you. Can you stop sharing your screen, please, so that I can start sharing? Yes. So, can you see my screen?
Yes, sir.
Yes, very good. Thank you. Well, okay, thank you once more, and welcome everybody. Thank you also for inviting me to present a lecture in the series of lectures in your institute. It's a real honor, and it's wonderful to see so many people interested in the topic. From what I understand, this is not the first lecture on electron diffraction that you hear, so I laid up the presentation so that I present only a very brief introduction, just to ensure everybody's on the same page. But then I will focus most of my presentation on showing you examples of what 3D electron diffraction is able to provide in terms of various types of problems, crystallographic problems that we may need to address. So to start somewhat lightly, this is a flowchart of the traditional approach to solving unknown crystal structure. So, okay. So when you start from unknown crystal structure, the first question a crystallographer asks is if he or she can grow big enough crystals. And if yes, then the question usually boils down to solving the structure with X-ray single crystal electron diffraction, only if there are some specific problems like magnetic properties or the need to distinguish study in detail hydrogen atoms and so on, then a use of neutron diffraction is also an option, but in the vast majority of cases, single crystal X-ray diffraction is the method of choice. And then, well, usually we get to the successful structure solution. The problem was, or used to be, when we cannot grow big crystals. In that case, the only option we had was powder X-ray or powder neutron diffraction, which is a technique that achieved many successes, but in terms of structure determination, it is limited, and it's very hard to solve complex crystal structures from powder diffraction data only. So since recently we can change this part of the flowchart by adding another decision point, can we use electrons? So can we use electron diffraction? And if we can, then we should use single crystal electron diffraction approach to solve crystal structures. And that, as you will see, gives us much higher chances of solving the structure. And only if we cannot use electrons, which usually means only the case when we need to do diffraction in environments like high pressure or in gas or liquid environment. Only in that case, we are really forced to use powder X-ray or powder neutron diffraction. So that's the difference, the change that we face in crystallography in the past, say, 10 to 15 years. And I think it's really important to spread this knowledge that 3D electron diffraction can provide us crystal structures that were until recently unreachable. So when I speak when I use the word electron crystallography, in general, it means a scientific field that retrieves crystallographic information by using electrons as a radiation probe. That's a very general definition and includes, for example, also high resolution transmission electron microscopy and many other related fields, spectroscopy, but in a strict sense, electron crystallography is crystal structure determination by means of electron diffraction. This was long believed to be extremely difficult or almost impossible in general, and only in the year 2007, after the first publication of Ute Kolb from the Mainz University, that opened the door to making this possible. And since that time, since 2007, there were many variants of the general approach proposed under different names. So you can find names like ADT, automated diffraction tomography, or EDT, electron diffraction tomography, RED, rotational electron diffraction, micro-ED, microcrystal electron diffraction, and all these terms refer essentially to the same method, only with slight variants of how the experiment is performed. And therefore, in a review paper in 2019, there was an umbrella term proposed 3D ED for 3D electron diffraction, because this is a term that does not refer to any of these particular specific flavors, and at the same time it captures the key property of the method we are using, and that is that it's electron diffraction, and also that it is collecting 3D data. That's what makes this method different from the previous ways of collecting electron diffraction data, which were mostly focused on collecting single patterns and therefore collecting only two-dimensional and not three-dimensional data. So what makes this approach so attractive? Because electrons interact very strongly with atoms, they allow us to analyze really small crystals. But the price to pay is the necessity to deal with multiple scattering. We will come to that later. That is, of course, the key part of the problems, but also success of the method. But when I say we can deal with small crystals, that means really small. For crystallographer, really small crystals, like, for example, here, this crystal has maybe about 100 nanometers, the smaller dimension. And this is a perfectly well-sized crystal for 3D ED investigation. But we can actually go down even more. This is a crystal which has just a little bit more than 10 nanometers in this shorter dimension, and it was still used to collect complete three-dimensional single crystal diffraction data. The principle of the technique is very simple. It's very similar to X-ray diffraction data collection. So we take a crystal without particularly orienting it in the beam. We shine a beam of electrons through it, and then we rotate the crystal either continuously or in steps. and record the diffraction patterns as the crystal rotates, as you see here. And then as a result, we can obtain a three-dimensional reconstruction of the diffraction space or reciprocal space, and well, that's then hence the 3D electron diffraction method. So the principle is very simple. There are certain experimental challenges that need to be overcome related to the stability of the crystal. You can imagine that keeping a crystal that is 20 nanometers in size in the beam is while rotating plus minus, say, 50 degrees is a challenge. But these are experimental difficulties that have been to a large extent overcome in the past years. So now we can say that a reliable and quite robust data collection protocol is available, and we are able to collect this kind of data essentially routinely. As I mentioned, the consequence of having strong interactions of electrons with crystals is that we face so-called dynamical diffraction effects or multiple scattering effects, dynamical diffraction. On this slide, I outline just the basic principles or basic difference to the established kinematical approximation. So kinematical approximation, that's an approximation that each quantum of radiation, X-ray or electron, scatters at most once in the crystal. And that is an approximation that's very well valid for X-ray diffraction data or neutron diffraction. And then in that case, there is a simple relationship between intensity of each reflection and the corresponding structure factor. So the Fourier transform of the electron density, and we can say that that the intensity is proportional to the square of the structure factor amplitude. It's a very simple relationship which makes the structure analysis from X-ray diffraction data relatively simple and straightforward. On the other hand, with dynamical diffraction theory, things are different. And the reason is schematically shown here on the right side. So this is a schematic diffraction pattern of an oriented crystal as seen on the detectors. So this is the central or transmitted beam, and these should be individual diffracted beams. But the problem is that if the interaction with the crystal is strong, then each of these reflections can in turn act as new primary beams. And then there is a new primary beam, for example, here, and around this reflection as a new primary beam, there is a whole new diffraction pattern emerging. So you can imagine that now the diffraction pattern is not created around the original beam, but around the diffracted beam. And these two, of course, overlap. And this is true not only for this reflection, but for all other reflections in the diffraction pattern. And this can happen not only for twice, but it can happen 3 times, 4 times. So it is a very complicated process. Luckily, there is a well-developed theory that allows us to calculate the diffracted intensities even in these complicated cases. And these 4 steps essentially outline all you need to do to calculate diffracted intensities in dynamical diffraction theory. I will not go through the details. This is just an illustration showing that if we know the structure, we can calculate the structure factors. And if we know the orientation of the crystal, we are able to calculate the diffracted intensities within, including the dynamical diffraction effects, to a good precision. Now, we can do it, so we know that it is possible to do the dynamical calculations, but that doesn't mean that it's always used in the structure analysis, this knowledge. There are various ways of dealing with dynamical effects in crystallographic analysis using electron diffraction, and I will only briefly outline the 3 main approaches. So we can either try to average the refraction effects out, we can try to, the dynamical effects out, we can try to correct them approximately, or we can take them into account in the calculations. So when talking about averaging, averaging helps a lot when it comes to suppressing the dynamical diffraction effects, because the effects depend critically on crystal orientation and they can vary sharply. So if you average the diffracted intensities over many crystal orientations, there is a chance to smooth out or average out the dynamical effects. That works reasonably well, but it's important to keep in mind that this approach does not remove the effects completely, no matter how much data you average. A simple demonstration that this is true is can be seen in the analysis of systematic absences. If you have a crystal that has so if the crystal has symmetry that leads to kinematically forbidden reflections, so systematic absences, these absences may be violated due to dynamical diffraction effects, as shown in these pictures. So this is a picture, this is the refraction pattern of the same crystal at two slightly different orientation angles. And here in this row, you can see that every second reflection is missing. So this is a systematic absence due to a 2-1 screw axis. And here, when we are close to an oriented pattern, you see that there are additional reflections that break the systematic absences. And these are purely resulting from dynamical effects. And of course, once they are there, no averaging will bring the intensity back to exact zero. Even if you do a lot of averaging, there will be some non-zero intensity in these forbidden reflections. There are various options or various ways of averaging the data. Either during the data collection, you can average by applying continuous rotation to the crystal, or you can use so-called precession electron diffraction, which is a special geometry that force or makes the beam move on a conical path. But also post-data collection, you can do the averaging by simply averaging over several data sets. And recently this trend seems to be emerging. So for example, this here is an example of a crystal structure determined very nicely. So all atoms are there, even hydrogen atoms are visible here in the difference Fourier map. And this data was obtained by averaging, or this structure was obtained by averaging data from over 200 crystals. So that is an option, but on one hand, or first, it's not always practical to collect data from so many crystals, and secondly, sometimes that is not even available. There might be cases where there is just a few grains. Typically in geological materials, you find only a few grains of a material, and we don't have access to hundreds of crystals. But if that access is available, this is one option. The second and non-exclusive option, of course, we can use one on top of the other, is an approximate correction, which is known in X-ray diffraction or X-ray crystallography as extinction correction. Extinction correction is a simple correction for small dynamical effects used in X-ray diffraction, and therefore it's also an obvious thing to try for electron diffraction. And indeed, sometimes it helps quite significantly. For example, in this refinement of the molecule of carbamazepine, which gives an R factor of 24% when extinction is not applied and only kinematical approximation is used. And with extinction applied, we obtain a significant improvement of the R factor from 24 to 18. But it's only an approximate correction, and the dynamical effects in electron diffraction are not weak, they are strong, and that means that the extinction correction is not really suited for this kind of of dynamical effects. So sometimes it helps, but not always, and not completely. So then finally, of course, the best approach to dealing with dynamical effects is to take them into account. The theory is here, so why not using the theory to calculate the expected diffracted intensities using the dynamical refinement. It brings a number of advantages over kinematical refinement, so over the case of ignoring the dynamical effects. One of them that is shown here in this plot is improved fit, so better accuracy of the fit. These are 8 structures carefully refined kinematically and dynamically, and this is a histogram of R factors obtained with the kinematical refinement. So you see we are somewhere between 10 and 18%. And this is actually a very good set. So typical values for kinematical refinement are rather somewhere here around 18% or 16 to 18%. And then when dynamical refinement is applied, the R factors which express the quality of the fit they drop significantly to something like on average 7.5 or 8%. But of course, that's just an R factor, that's just a number, but what counts more is the accuracy of the structure model, which is, as we will see, significantly improved. The dynamical refinement is more sensitive to weak signals. And importantly, it does not require a special data collection. So it's possible to apply it to the same data that were collected for kinematical refinement, or there is no difference in the experiment. Currently, it is available only in the software IANA 2020. So if for people used to OLEX2 or Shellix, this means learning another crystallographic software. But of course, the principles of the refinement are the same. And the price to pay is that the dynamical refinement takes somewhat longer than kinematical refinement. And here are 2 examples. One is a very simple structure with 6 independent atoms and small unit cell. There you see that one refinement cycle takes just a few seconds. If you have a larger structure with 86 independent atoms and the volume of the unit cell of 3000 cubic angstroms, so that's not a very large structure, but it's already somewhat sizable, then you see that one refinement cycle on a good personal PC takes about 1 minute or a bit more than 1 minute. So that's definitely longer than the kinematical refinement, which takes a second per cycle or maybe a fraction of a second, but it is still feasible. Now, as I said, the important thing is not the R factor, but the quality of the structure model and the details we can see. And here I show 2 aspects of the improvements. On the left side, you see the improvement in the difference potential density. So in electron diffraction, what we see in the Fourier maps is not electron diffraction, but it's electrostatic, sorry. It's not electron density, but it is electrostatic potential. That's why we speak about potential maps and not electron density maps. So in these potential maps, in the difference potential maps, we are looking for weak signals. And of course, we want to have flat maps with no noise or as little noise as possible. And their dynamical refinements really brings a large improvement, as seen in this difference potential map for mordenite, which is a zeolite. And on the left, this is the difference map from dynamical refinement, and on the right from kinematical. And you see the amount of noise that drops significantly when going from kinematical to dynamical refinement. And on the right, an example of the refinement of an organic material. So this is a molecule of paracetamol, where the kinematic refinement goes or gives you the right connectivity, but the errors on the bond lengths are relatively large, with root mean square deviation error of 0.04 angstroms.
Sorry, Vivek, can you mute all other people?
Yes, sir.
Okay, thank you. So the root mean square deviation is about 0.04 angstroms, which is relatively large. It's more than a difference between, it is comparable to the difference between a single bond and double bond. So it may cause troubles in chemical interpretation. When we move to dynamical, the root mean square deviation drops down to just about 0.01, so significantly better. So with this introduction, let's move to the examples. So here is a little summary of what we can and what we cannot do with 3D electron diffraction. So we can do a lot. We can solve structures that remained unsolved for a long time, including very complex structures. We can see weak signals like hydrogen atoms. We can determine absolute structure, even for light atom structures. And we can even, as you will see, do charge density studies using electron diffraction data. What we can't do is collect data at high pressures or in specific environments. Electron diffraction data are collected essentially exclusively in vacuum. We can't collect highly redundant data on a single crystal because we have only a limited range of tilt in electron microscope. And for now, we can't reach the same accuracy as single crystal X-ray diffraction, despite of the improvements brought by dynamical refinement. This is another histogram of R factors. Red is a collection of R factors from a broad number of materials, from organic to inorganic. You see that the spread is rather large. When we move to or switch to dynamical refinement, things improve considerably, and most refinements approach the level of, say, 10 or below, the 10% or below. But the green set here is a selection of X-ray refinements, which have an average R factor of around 4%. So we are still about a factor of 2 in the quality of the fit we can reach. But this is hopefully also something that will improve in the future. So now I'm coming to the examples. The first example is one that I like a lot. It's a very simple structure. It's tantalum trisulfide, and it is it's been thoroughly studied for decades. There are hundreds of papers on TAS3, and yet its crystal structure has not been known because it forms, as you can see here in this picture, these very plastic exfoliated bending small crystals, which were impossible to grow in big enough quality, large enough size and good enough quality for single crystal X-ray diffraction, and it was not possible to solve the structure from powder diffraction either. With electron diffraction, this was a matter of one day to solve the structure, because here, even though the crystal is very bent, it's possible to collect data from maybe this part here, or even from some small part of the crystal like this, and it was possible to solve the structure relatively easily, and so finish really decades of uncertainty about the crystal structure of this material. And even better, at low temperature, this material is modulated. So it has a charge density wave structure with a modulation vector. You can see the modulation here. These are the small spots next to the main reflections, and it was possible to determine even the modulated structure with electron diffraction. The next example comes from the field of framework materials. This was a collaboration with a group of Svetlana Mintova in Cannes, in France. They produce zeolites for various applications, and in this case, they produced specifically nano crystals or very small crystals, as you can see here, and they analyzed the absorption capacity of that material with respect to absorbing CO2 and selectively absorbing CO2 and not methane. And the crystallographic question was, can we see the place where the CO2 molecules are absorbed in the structure? So we measured the data with or the crystals with electron diffraction. This is the crystal structure solution. So these yellow blobs here represent the framework atoms. This was straightforward, but also nothing new. This was known, the structure. But then looking in the cavity, we were indeed able to see the difference potential corresponding to the CO2 molecules. It was clear that one of the ends of the CO2 molecule is relatively strongly bound to the cation sitting here in the cage. But it was really possible to determine the position of the molecule. We could calculate that there are at most 9 CO2 molecules that can be absorbed per unit cell of the material. And indeed, the experimental absorption capacity turned out to be about 8 CO2 molecules per unit cell. So very, very high absorption capacity experimentally, very close to the theoretical limit. And that was, of course, possible thanks to the nanocrystalline nature of the material. So the surface to volume ratio was very high. The next example is still relatively recent. It is a mineralogical example. This is a material that was found in Russia and Soviet, in Russia, in Kola Peninsula in the north of Russia. And it's a mineral that has been again known for a long time, and it's been known to be very complex. The structure determination was impossible because you see these very, very fine fibers, and this is a crystal seen in a transmission electron microscope, so really submicron crystals. And in the formula, in the estimated formula, you see that the complexity of this mineral is really large. But when looking at the refraction, this is what we saw. It diffracts beautifully. It shows that despite of the complexity, the structure is very, very well ordered. And indeed, it was possible to solve the structure just with standard approaches. And this turns out, and this is the structure. It turns out to be one of the 10 most complex mineral structures known to date, with 360 independent atoms, so over 700 atoms in the unit cell. And the nice, bonus in this investigation was that a colleague from Germany was able to collect high resolution transmission electron microscope images. And these, okay, so sorry, I forgot to mention that this is some kind of a nanotubular material which forms channels along this direction. But then these are the high resolution images. And you see the first stunning thing for me was that there are no defects here. Everything is perfectly ordered. Despite of the incredible complexity of the structure, there are no stacking faults, nothing like that visible in this image. And second, of course, it's hard to see immediately now for you, but when we overlaid the structure over the electron microscope images, it turned out that the match is perfect. So every single dot in this high resolution image corresponds to one cation in the structure determination that we performed. So that was that was very satisfactory, of course, and it's also a nice reminder that electron microscopy is more than just diffraction. Even for crystallography, it's useful to keep in mind that electron microscopes can provide even direct images of the structure. They can provide spectroscopic information. So there's a wealth of information available together with the collection of the three-dimensional electron diffraction data. So I mentioned that one of the advantages of 3D electron diffraction is, and especially dynamical refinement, is that we can see weak signals in crystal structures. Of course, the weakest scatter is hydrogen. That's true both for X-ray diffraction and also for electron diffraction. But in electron diffraction, hydrogens are relatively heavier compared to heavier atoms than in X-ray diffraction. That can be seen here on this plot. So this is the relative scattering power of hydrogen compared to carbon. This is in percent. So while at low angles, but there are very, very few reflections at low angles, so this doesn't really count so much. So at low angles, the scattering power is similar, but then while the scattering power of hydrogen goes down with the scattering angle very dramatically, for electrons, it remains essentially constant. And therefore, hydrogens are in principle better visible in 3D-ED than in X-rays. Despite of that, it's been for a long time considered difficult, but nowadays it's almost routine. But there is an interesting aspect to be aware of when refining hydrogen atom positions from electron diffraction. You probably know that in X-rays, if you freely refine hydrogen position, it will refine to the distance to its parent atom or bound atom, carbon, nitrogen, or oxygen. It will refine to a distance that's significantly shorter than the nucleus distance by about, say, 0.1 angstroms. For neutrons, if you do neutron refinement, then the distance will be the right nucleus distance, because neutrons are sensitive only to the nuclear positions. So the question comes, what about electron diffraction? And the interesting outcome is that if you refine freely hydrogen positions from electron diffraction, the position will be slightly longer than the nucleus distance. And the reason is that electrons are sensitive to both the negative potential of electrons and positive potential of the nuclei. So if you shift the negative potential of electrons towards the covalent bond and keep the nucleus where it is, then the total sum, positive minus negative, will shift a little bit away. So it will shift a little bit away from the nucleus, and here is a plot of these shifts for various compounds. So these are the molecular structures of the compounds. These yellow and orange maxima in the difference map show the positions of hydrogens. So you can see very clearly that, or you can see that we can see the hydrogens very clearly. And this is the difference of the hydrogen positions from the expected nuclear position. And you see that in some cases, it's almost exactly spot on, but in most cases, there is an elongation of the bonds, and the largest elongation is seen from cobalt aluminum phosphate, which is this compound here. And for the hydrogens in the water molecule in natrolite, which is here and there, the difference can be up to 0.15 or even more than 0.15 angstroms. So that needs to be kept in mind, that hydrogens may refine to distances larger than expected. The next example shows how important it is to see the hydrogen atoms. It is a bit of an anecdote, but I'll present it anyway. This is a co-crystal of empagliflozin and proline. And the question here was to test or confirm that this co-crystal is indeed a co-crystal and not a salt. So if it was a salt, that would mean that one of the hydrogens of one molecule would shift to the second molecule, making one molecule negatively charged and the other positively. So that was so our task was to exclude this possibility. So what we did, of course, was to remove the hydrogens that might be possibly cleaved away and moved to the other molecule, and see if we can see the positions of the hydrogens in the difference Fourier map. And this is indeed what we saw. So all the hydrogens are or were where we expect them to be, some of them rather weak, but most of them pretty nicely visible exactly where they should be, like here, 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 and here. So that was easily done. But the surprise came on the other side of the molecule where we did not expect any problems. So this was the expected structural formula. This is the same, just rotated to match it with the experimental data. And here you see there are two very clear maxima around an oxygen atom, which would make this oxygen 4 bonded, which is an obvious nonsense. So after a little bit of investigation, it turned out that this molecular formula, which came from Wikipedia, was actually wrong. The oxygen should not be here, but here. So not here, but here. And then, of course, this becomes a carbon with two hydrogens, and this becomes an oxygen. But without really seeing these two difference maxima, it would not be so easy to spot that mistake. Nowadays, the Wikipedia entry on empagliflozin is already corrected. Now, seeing hydrogens on organic materials is probably not so exciting. Hydrogen is really a significant part of the scattering power in these materials, but thanks to the relatively large scattering power of hydrogens compared to heavier atoms, it's possible to see hydrogens relatively easily also with heavier atoms. And one of the examples is here. This is another mineral. It has a very tongue twisterish name, kyatialite. It's iron arsenate, and it contains a lot of water and OH groups. And it turns out that the structure contains a lot of hydrogens, 22 independent positions, out of them 12 are disordered. So all these half-colored, half-shaded positions are only half-occupied hydrogens. And it was possible to determine the structure completely, including all these partly occupied hydrogens with dynamical refinement from electron diffraction data, and it was not seen at all in the X-ray diffraction data. Although admittedly, this was an investigation from 1981, so probably today it would be a different story. But still, we were quite pleased to see that the electron diffraction data provided very clear picture on the positions of even the disordered hydrogens. And if hydrogens next to arsenic still do not impress you, then there is the structure of Viacheslavite, yet another mineral, or Gladys Stetsiuk, our colleague, is specialized on mineralogical samples and their analysis by electron diffraction. So this is a uranium-containing mineral. So this atom here is mostly uranium, surrounded by 10 oxygens. And in this case, one of the oxygen atom has a hydrogen atom bonded to it. And again, you can clearly see the site of the hydrogen in the difference map. So that was the story of hydrogen atoms and demonstration how efficient can electron diffraction be in spotting hydrogens. And the next example is absolute structure, or next topic of my presentation is absolute structure. Just again to make sure everybody is on the same page, a few words on what do we mean by absolute structure and absolute configuration, and why is it important. So by the definition from Online Dictionary of Crystallography, absolute structure is a specification of the orientation of a non-central symmetric crystal structure under the operation of inversion. In simple terms, determining if we have a left hand or right hand orientation of our structure. An example: quartz, silicon oxide, very common mineral, crystallizes in a chiral space group, and it can have either a left-handed 3-1 screw axis P3-1-2-1 or right-handed screw axis P3-2-2-1, and these two are distinct, and so that the term absolute structure specifies the difference between these two. On the other hand, absolute configuration relates to finite objects and specifically to molecules that are non-centrosymmetric, that contain chiral centers. This is an example. This is an amino acid, L-proline and D-proline. These two are mirror images of each other. And the link between absolute configuration and absolute structure is that if you crystallize a chiral molecule into a crystal, then determining the absolute structure of the crystal allows the determination of absolute configuration of the molecule. And that is what we are usually interested in, because the chirality, so absolute configuration, is of course extremely important in biological or biochemical related research, because of course it's not necessary to emphasize that essentially all the molecules that work in our body, proteins, hormones, and so on, they are chiral, and so the chirality is an important aspect to know. Unfortunately, determination of absolute structure by diffraction is all but easy. The reason is that the diffraction is, to a good approximation, centrosymmetric. That's called Friedel's law, and it means that within kinematical approximation, without any other information or any other effect, the absolute structure cannot be determined purely from diffraction. Luckily, there are effects that break this Friedel's law, this central symmetricity, and in X-rays, this effect is called resonance scattering, and it shifts the phase of photons scattered from electrons and therefore breaks Friedel's law. Unfortunately, this breaking is very weak. Here are a few numbers, so that the breaking depends on this on the phase shift induced by during the scattering process, and that phase shift depends on the wavelength and on atomic number. And for small atoms like carbon, so light atoms, this effect is really the order of a fraction of a percent. And as a result, the diffraction from 1 and the inverted structure is almost the same, as we can see here on this plot of F-calc from one enantiomorph and the other enantiomorph. And you see there is almost a perfect straight line, so no difference. And only if we calculate the differences and look at the differences between the calculated structure factors of the two enantiomorphs, so the two absolute structures, only here we see very small differences that are again of the order of 0.1% or so. So it is possible to determine absolute structure with X-rays, but it is difficult and you need really good data, especially for all light atom structures. On the other hand, for electrons, the effect that breaks the Friedel's law is dynamical diffraction. And the amount of breaking does not depend on the atomic number. It's equally strong for light atoms and heavy atoms, and therefore it's possible to determine the absolute structure equally well from weak from light and heavy atoms. And even better, the effect is large. So if you recall this plot for X-rays, the scale here was around 0.1, 0.2. for the scale in hundreds on the horizontal scale or horizontal axis. And here on about the same horizontal axis, we have here the differences that reach up to 50 or even more. So the effect is of essentially the same order of magnitude, or at most one order of magnitude less than the actual amplitudes. And that's why it is much more easy to determine absolute structure from electron diffraction than from X-rays. So this is a very busy plot, but it is a plot taken from a recent publication by Paul Klar, a former postdoc in our group, and of course other people. That was published last year, and it focused, among other things, on the analysis of absolute structure determination. And this slide combines the results of many refinements. So each column here is one refinement on one data set of a chiral compound, and it illustrates the robustness of the structure of the absolute structure determination simply from the difference of the refinement R values. The red point is the R value for the wrong enantiomorph. The green point is the R value for the correct enantiomorph, and you can see that in most cases the differences are so clear that simply by looking at the R factor we can determine the absolute structure reliably. And on top of that, it's possible to do a statistical evaluation of the differences. These are these weak pink bars, and they show you the reliability of the absolute structure determination, in which is in most cases exceeding the statistically significant level of 3 sigma. Just one specific example. This is a natural product isolated from a fungus, Cordyceps javanica. Natural products are often investigated because they are potential drug sources for new drugs, but they also have notoriously complicated structures and unknown chirality, because it can be really anything, and they are usually available or often available in very small amounts because they need to be extracted from biological material. So this was one such case. It's a cyclopeptide which has mostly S centers of the chiral carbons on the cycle, but one of them is R. And in this case, even though the molecule is relatively complex and the data were not of a super great quality, it turned out that, again, the absolute structure can be determined very easily. And the statistical significance in this case, the combined reliability was 23 sigma, which is really extremely high value. So extremely high reliability associated. And finally, I see that the hour is almost over, but I want to say a few words about probably the most challenging crystallographic investigation you can think about, and that is charge density analysis from diffraction data. So the charge density analysis means seeing effects of interactions between atoms, effects of electrons moving from one atom to another in ionic bonds, or electrons shifting in the covalent bond for covalent bonds. And here, again, at least in theory, electrons are better positioned to allow this analysis than X-rays. This is shown here in these plots, which show the relative difference in scattering power between several ions, so oxygen, oxygen -1, sodium, sodium +1, and so on. And the green curves, excuse me, the green curves show the difference in scattering power for electrons, and the orange curves for X-rays. And you can see that at very low, so on horizontal axis, there is a diffraction angle or length of scattering vector in reciprocal angstroms. So at very low scattering angles, electrons are always better than X-rays. And see always that the green curve is above the orange one. But even at medium angles, as we go to heavier atoms, sodium, chlorine, iron, and europium, we can see that to more heavy atoms we go, the larger is the advantage of electrons over X-rays in seeing the difference between charged and uncharged atoms. And this has been also demonstrated on a series of compounds. These are just 3 examples. On the left, zeolite named natrolite, where here the the surplus of electron density is shown with yellow isosurfaces, and the depletion is shown in blue isosurfaces, and you can nicely see how the cations like silicon here are depleted in electrons, and the anions, oxygen here, have more electrons. And on these in these 2 slides, or these 2 images, this shows the so-called multiple refinement, so a full refinement of the deformation of electron density in the crystal due to interatomic effects. And here you can see how the refinement really can determine the shift of the electrons into the covalent bonds, or here the accumulation of electrons around oxygen atom. So I don't want to say that this is easy or even routine. It is really challenging. It requires really very good quality data and careful analysis, but it shows that it is possible to do these really, really challenging refinements, analysis, even with electron diffraction data. And just as a last example, it is even possible to do this with very heavy atoms, like in this case, lutetium. So with this, I come to the conclusions. So I want to just reiterate that nowadays, almost any structure can be solved by 3D electron diffraction. There are no limits on complexity. Even protein structures are being solved nowadays. I haven't spoken about macromolecules because this is not my field of expertise, but there are people analyzing also macromolecular structures with 3D-ED. The largest complications are the dynamical effects, but they can be treated to a large extent, and that leads to more accurate results, finding light atoms, even in presence of heavy atoms, and determining absolute structure of non-centrosymmetric materials. And very importantly, since a few years now, there are dedicated instruments available on the market that are available for purchase, and that make it possible for users that are not specialized electron microscopists or no specialized crystallographic laboratories to get these machines and start collecting data and solving crystal structures in their chemistry or material science related lab. There is still an R factor and accuracy gap between even the best electron diffraction refinements and X-ray diffraction refinements, and this is something that still needs to be investigated and hopefully closed in the future. But that is a work in progress. With that, I want to acknowledge especially the members of my group. They are numerous, and many of them contributed also to the results that I presented in this presentation. I acknowledge the funding, and I thank you for your attention.
Fantastic. To me, I really enjoyed this presentation. Beautiful.
Thank you.
I get this idea. I mean, I get this feeling that it's very complex minerals, everslogite. I was so amazed to see that kind of complex mineral is really every atomic position is fixed in that. And you are showing an electron micrograph with no defects.
Yes, that's really amazing. Yes.
Now, I just wanted to check with you whether these kinds of complex structures with no defects, have you seen any of them before, or this is some unique example?
Well, I myself not doing a lot of high resolution imaging, so I can only speak from experience with others' work, but it is not standard, but it is not really uncommon. The important aspect here is that it is natural material that had literally thousands of years to grow. Also, that was a slow process, and there was enough time for the material to really crystallize and stabilize in the thermodynamic minimum, so to say. So that is, I think, very important aspect, the time that it took to produce this mineral. And also, I should emphasize one more thing: there are defects, but they are in the plane perpendicular, or in the plane perpendicular to this view. So it's twinned. The material is frequently twinned, but the twinning does not affect this view. So there, but nevertheless, the degree of organization of this mineral is really amazing.
Very nice. You touched upon this dynamical effects and the need to have improved analysis with the kind of software that you talked about. I wanted to know, does it also mean that crystals that you study should be of an optimum dimension so that multiple diffractions or scattering do not occur in a given sample? Does it put any restrictions on the sample?
In general, the smaller the crystal, the better. In terms of dynamical effects, of course, the thinner the crystal, it's the thickness that plays a role. So the thinner the crystal, the less chance there is for multiple scattering. So the less dynamical effects there are. However, even in nanoparticles as small as 10 nanometers in diameter, there are measurable and appreciable dynamical effects. So you can't say that if you pick crystals smaller than, I don't know, 50 nanometers, that you will essentially suppress the dynamical effects. That's not how it works. In practice, we usually do not have that much choice over the size of the crystals. And I can say that the proper treatment of dynamical effects allows getting good refinements even from structures that from crystals that are relatively thick. So crystal that is 150 or 200 nanometers thick, that's already a relatively thick crystal for electron diffraction, and even then, in there it's possible to get sometimes good results. Maybe another additional remark. What is more important is the crystal quality. It's really important to pick good quality crystals, and it's not always obvious. We can measure small crystals, that's a great advantage, but we still need good quality crystals to get good quality result. This is the same or common to X-ray diffraction, and it's not always, unfortunately, not always possible to get good crystals.
Great to see this, variety of data, a variety of systems that you talked about. You also mentioned about the limitation. But then even with such limitations, I see that, of course, you can do temperature-dependent measurements. With the current kind of microscopes, you can do potential-dependent measurement, electrical potential. Maybe at some point in time, you can also do photons. I wanted to know from you as to what extent the subject area has expanded in looking at phase transitions and effects. You talked about charge density waves. So effects such as these, by varying potentials, looking at temperature, looking at radiation, are there a good quantum of studies with electron diffraction? And are they getting some new insights?
I think this is only emerging right now. I'm not aware of any electron diffraction studies under potential, for example, but there are, of course, temperature-dependent studies that is relatively easy to do in a range of temperatures. There are sample holders which allow you to reach from, say, liquid nitrogen temperature all the way up to 800 degrees centigrade routinely, even more sometimes. So temperature-dependent studies are possible, and definitely also studies under electric field would be possible, or even there are also people trying to go in the time-resolved area. So then pump probe experiments would also be possible. Here, I think that certain care needs to be, certain care is needed because electrons, because of their strong interaction, they themselves induce changes in the crystals. Luckily, they are not so big to destroy the structure, at least not immediately.
Yeah.
But there might be a problem when doing, for example, pump probe experiments in excited states with photons. I think there could be a difficulty in the electrons interfering with this. But in general, there is a lot of potential there, and I think this is only now a field that after the electron 3D has been proven to be really versatile and reliable, now the field is open to doing all these advanced crystallographic studies with it.
Thank you. I would leave it to others.
So I have one question.
Mm.
You have discussed about averaging data. Is it same like merging data from various crystals?
Yes, that's what I meant. Yeah.
And another question is, which software you use to process these 3D data?
So here in Prague, we develop our own software. It's called PETS2. And so we use that software to process the data. The software is available, so anybody can use it. It is one of the few options that are out there. It's also possible to use XDS or Dials. These are two very popular programs. And also, if you are there is Crystallis Pro software that is familiar to Rigaku users, but PETS2 is so far it has the special feature of producing data suitable for dynamical refinement, which XDS does not, and Crystallis Pro does. So if you use Crystallis Pro, it's also possible to get data for dynamical refinement. And since recently, also Dials has this option, but it's very experimental.
Thank you, sir.
Deepak, can you please take care of this? There may be others to ask questions. Please moderate it.
Yes, anyone have any other question? So I have just one question about regarding if a crystal have a different multiple domain in the same crystal, so can we get the information about the domain in the same crystal?
Well, so multiple domains that can be either due to simply an intergrowth of two or more crystals together in some non-oriented way, or you may also mean twinning, which is like some ordered or not ordered, but defined, crystallographic defined intergrowth of 2 or more domains. But in both cases, the answer is yes. Yeah, it's possible to do that. It is again just like for X-ray diffraction. Of course, it's better to have a single crystal if you have overlap of domains, either by twinning or by random orientation. There are complications of overlapping intensities that need to be handled, but all this is not different between X-rays and electrons. So in principle, it is possible to deal with such crystals. But as I said, the best results are obtained from the best crystals, and one of the features for a good crystal is that it is alone in the beam. So that's of course always preferred.
Okay, thanks. Regarding if a crystal having the system having the different polymorph, so at a time when we are doing the 3D, can we differentiate the different polymorph at a time or not?
Yes, this is one of the very good or perfect use cases for electron diffraction. If there are more polymorphs, sometimes they are intergrown, but because you can pick a small particle with electrons, there is a good chance that you pick only one polymorph, or only at least a particle that has a larger proportion of one polymorph than the other. So yes, polymorphic screening is one of the applications where electron diffraction plays a stronger and stronger role. And there have been many cases already reported where electron diffraction allowed finding polymorphs that were not visible in by X-rays or powder X-ray diffraction, because they were minor, so a small amount. But with electrons, you pick that crystal and you solve the structure even from a polymorph that is 2, 3, 4% of the total volume.
Okay, thank you. Anyone have a question?
No. Seems that I was very clear in what I said.
Certainly, it was quite clear, and it's just that it opened up a large number of possibilities for the kind of systems that people are working on, and that would ultimately more and more of such systems, if we investigate more and more problems, more and more ideas will come. And that's what your study has essentially thrown open, the diverse possibilities. So only thing that I would say is that maybe we can, of course, we do collect data. We are just beginning to do this in our laboratory. Now, that opens up a whole lot of data, but a lot of support is required wherever problems arise. And at the same time, the kind of insights that one may have could get additional, I would say, structural insights from the available data themselves. So those are distinct possibilities that I see. And what it means is that somebody has to spend some time as a sort of an interface between your group and what is going on here. And then something very new could come out.
Yes, absolutely. And if you consider venturing into this field, as I understand you are, then I'll be, of course, more than happy to assist, to provide some guidance or help with troubles, or also other people from my group will be happy to help. So don't hesitate to contact us and ask for help, because I know that the beginnings can be hard. It can take some time to get over the initial stages and learn the procedures, as with any other method. But once the procedures are in place and the experience is there, it is relatively easy, and from my experience, I can say that really the new results and the qualitatively new results that you can get, it's really rewarding and worth the effort spent on the initial stages of learning the method. So I'm most happy to help, and don't hesitate to reach out.
Thank you. Thank you. That is one of the reasons why Deepak is there with sitting with Monica. So obviously, you know, this kind of an effort that goes on, and Harshita, who introduced you, is getting exposed to electrons and electron diffraction now. And our people have been mostly doing imaging, and now they are getting more into diffraction. Well, Harshita, can you please conclude this?
Thank you so much, sir, for your time and efforts. And it was a wonderful presentation. Have a nice day.
Thank you. Thanks everybody for listening, and wish you best of luck. Have a nice day too.
Thank you.
Thank you.